Today we're going to see in the one junction with a couple of examples, one an electrical system and one a mechanical system here. So the first thing that we're going to do is to recognize what's common to both of those junctions and go on then for developing the block diagrams and the bond graph. So let's just go over here. We're going to have, in this case, on the electrical system, as you can see in here, you have basically the equation. It says that the voltage is equal to voltage of C plus voltage of R, right? And that you will say the current I is common to all three elements. Okay, so that means that the the current, you can say I of B is equal to I of C and is equal to I of R. Okay, so the question here is, how do we represent this kind of connection? And you'll say that all three currents, the current is common to all three, but the voltage of the source is equal to what? To the voltage of the other two. So that means that you can say what comes in equals to what goes out. So this is the voltage, the source equals to the sum of the other two voltages. So how should we do this in terms of a block diagram? In here you have a connection of the, let's say, of the voltage source, and then you have the equation of the, this would be the C element, and of course you have a connection to the R element on this side like this. All right. In the connection, it's saying basically that this would be the effort is the same. So whatever this is not the effort is the same, the flow is the same. So why don't we put here B of a C like this, and this will be I of C, this would be V of R, and this would be I of R. And this would be V like that, and this would be I of V like this. So the currents are the same. So this would actually mean that this connect like this, see? But the voltages are different. So it means that we are going to connect it like this, see? That means that you have a voltage that came in here equals to the voltage, the two voltage that got out here. Yeah. So this block diagram represents these equations. And what we need to do is find out a way to represent the same thing using the bond graph notation. So this is the actual block diagram. Okay. So we need to represent the, so there's the block diagram. We need to represent the bond graph model. So in here we go and we say, okay, this is a one junction in here. And then you're gonna have a connection that goes like this, where this is the voltage V, this is B of the capacitor, and this is B of the resistor in here. And what happens is that in this case the flow, it needs to be, the flow is the same, but the voltages will add. How do they add in here? You have it like this. Well, we usually use a half arrow, right? So let's be consistent with that and just use a half arrow here. And that is like this. When you have a bond graph model like this, you know that V is equal to B sub C plus B sub R, like that. And that is your bond graph model of this same thing that you see here is the block diagram. Let's take a look now at the mechanical system in here. It's very obvious that on this mechanical system, you see the summation of forces equals to mass times acceleration in here for this kind of element. You know, that's the Newton's law. So summation of forces, but the velocity B is common to this. Okay, so in this particular case, we add the forces, you know, the connection, and in this case, we also consider the velocity as the common variable. So if for the static, you know, for the static condition, just to study the connection, summation of the forces equals to 0. So in this particular case, you will see that F minus F like this, and then of course is minus W sine of theta, where theta is this angle here like this, like that. This should be equals to 0 like this for the static case. Yeah. Okay. In the normal direction they don't move, so we're not going to write an equation there. But you know that the velocity of the F is equal to the velocity of this, and is equal to the velocity of this omega sine of theta. And the way we represent this is by a block diagram that reflects such a thing, where you have the summation of the forces here. Let's see how many elements we have. We have 3 in there. Yeah. So in here you have the force here F, and then you have on this the other force like this F in here, and then the flow is the velocity here. On this other side also the velocity here, and on the side of the other equation, the other one, Also, we have, this would be W sine of theta, but the velocity is common to all three. So what we need to do is we'll say, okay, look, the velocity is common to all three, so I am going to join it like this, see? And this would be the common point. But the summation of this would be the other thing. So one is common, the other ones will add. And how would we do that? It says f is equal to little f plus g sine of, so it depends how it's written in here. If f is like this, and these are like this, yeah. So this would be minus, minus, and this plus. And this is the representation of this junction. But you can also use a 1 to represent the same thing. There is the one junction, and then you will have the force here, and then what do we put? F and B, and this W sine of theta, and then the velocity also. So in this particular case, only one determines the flow. Like if you put it like this, the other ones will have to be like this. In this case, too, we could do the velocity here, or yeah, it's gonna be the same graph if we do it that same way. But you could have one of these flows, but set the flow for everybody else. If it is like this, then this one will also have to be like this. See, it is flowing, and out of each one flow out. So this is the way we represent the one junction in the bond graph notation. Again, summarizing, this is a junction where we have all the flows are the same, but the efforts will have to sum. There can only be one bond that determines the flow. All the other ones will not. So in this case, you see if you have this one determines the flow, the others have to be this way. You have to be out. So that helps us distinguish between a zero connection and a one connection.